Welcome to Data Do Library. In today's video, we will talk about variation of parameters. Let's begin. This method will be used to solve second-degree linear non-homogeneous differential equations. First thing we're going to do is find y of c the way we would in a homogeneous differential equation, which means we're going to set the right side equal to 0. So we have y double prime minus 4y prime plus 4y equals to 0. We're going to write this as r squared minus 4r plus 4 equals 0. We're going to factor this. We have r minus 2 and r minus 2, which means we have a repeated root of r equals 2. Therefore, our y of c is equal to c1 e to the 2x plus c2 x e to the 2x. To find y of p, we need an equation u sub 1 times y1 plus u sub 2 times y2. Our y sub c gives us y1 and y2, and all we have to find is u1 and u2. To solve for u1 and u2, we're going to use Wronskian matrices. First thing we have to do is find matrix W. The first row of this matrix will be our functions y1 and y2, which are e to the 2x and x e to the 2x. The second row is just derivatives of the functions above. So derivative of e to the 2x would just be 2e to the 2x, and derivative of x e to the 2x requires a product rule. So we'd have first, which is x, times derivative of the second, which is e to the 2x times 2, plus second, which is e to the 2x, times the derivative of the first, and first is x, the derivative of that is 1. Now that we've found this matrix, we have to find its determinant. Determinant is found by multiplying the top left with the bottom right and subtracting product of bottom left and the top right. So when I multiply e to the 2x times 2x e to the 2x plus e to the 2x, and then I'm going to subtract product of 2 e to the 2x times x e to the 2x. Now I'm going to distribute, giving me 2x e to the 4x plus e to the 4x minus 2x e to the 4x. Notice those two cancel, and I am left with e to the 4x, which is my w. Next, I need to find W1. W1 is also a 2 by 2 matrix in which the first column is replaced by 0, and then function, I'm going to call this function g of x. So the non-homogeneous part of this equation, which is x plus 1 times e to the 2x. The right column stays the same as w, which is this one. So x e to the 2x, and then 2x e to the 2x plus e to the 2x. Once again, I'm going to find a determinant, which means I'm going to multiply 0 times 2x e to the 2x plus e to the 2x, which obviously gives me 0, minus product of the bottom left and the top right gives me e to the 2x times x plus 1 times x e to the 2x. So to simplify this, I have negative x e to the 4x times x plus 1. That is W1. Next, we need to find W2. To find W2, we will keep the first column same as W, which is e to the 2x and 2e to the 2x, but replace the second column. We're going to have 0 and my function g of x, which is x plus 1e to the 2x. And again, find the determinant, which we have e to the 2x times x plus 1 times e to the 2x minus 0 times this, which is obviously 0. So to simplify this, I have e to the 4x times x plus 1, which is my W2. Now that we have W, W1, and W2, we can start finding our U sub 1 and U sub 2. To find U sub 1, we're going to use U prime of U sub 1 is equal to W1 over W. Prime of U sub 2 is equal to W2 over W. These are derivatives, so once we find U prime of 1 and 2, we can integrate them and come up with our solution. So W1 is negative x plus 1 times x e to the 4x divided by W, which is e to the 4x. As you can tell, e to the 4x will cancel with e to the 4x. And once we distribute, we have negative x squared minus x. And that is my u prime. To find u sub 2 prime, we're going to divide W2, which is e to the 4x times x plus 1, divided by W, which is e to the 4x. E to the 4x cancels, and we are left with x plus 1 as the derivative of u sub 2. We don't need derivatives, we need u sub 1 and u sub 2, therefore I'm going to integrate those derivatives with respect to x, which is integral of negative x squared minus x dx. That will give me u sub 1, which integral of negative x squared is negative 1/3 x to the 3rd power minus 1/2 x squared. Then we would normally have constant of integration, which we're not going to do that in this case. Integral of x plus 1 dx is x squared, 1/2 x squared plus x, and that is just my u sub 2. So now that I have u sub 1, which is this, and u sub 2, which is this, I can go ahead and plug it into my y's of p, which gives us y's of p is equal to u sub 1, which is negative 1/3 x cubed minus 1/2 x squared, times y of 1, which was this function here, which is e to the 2x, plus u sub 2, which is 1/2 x squared plus x, times y sub 2, which is x e to the 2x. Now we're going to simplify. So first I'm going to distribute e to the 2x through this parenthesis, giving me negative 1/3 x cubed e to the 2x minus 1/2 x squared e to the 2x. I'm going to distribute x e to the 2x through this parenthesis, giving me 1/2 x cubed e to the 2x plus x squared e to the 2x. I'm going to look for some terms that we can combine. The first one that stands out is negative 1/2 x squared and positive 1x squared e to the 2x. When I add those, I have 1/2 x squared e to the 2x. Next two terms are x cubed e to the 2x, and we have x cubed e to the 2x here. Therefore, negative 1/3 plus 1/2 is just 1/6 x cubed e to the 2x plus this part, and that's going to give me y sub p. Finally, the general solution is just sum of y's of c plus y's of p. So my y sub c was c1 e to the 2x plus c2 x e to the 2x plus my y's of p, which is 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. Let's do one more example. The first thing you should notice is that we can factor out the 4 out of this left side of this equation, leaving us with this. I can now divide both sides by 4, giving me the equation y double prime plus 9y is equal to 1/4 cosecant of 3x. And now we can go ahead and follow the steps from before. One difference is that y's of c is now going to have imaginary roots. Because if I write this as r squared plus 9 equals to 0, my homogeneous equation, I have r squared is equal to negative 9. So r is equal to 0 plus or minus 3i. Now 0 is my alpha, 3 is my beta. So y's of c is equal to c1 cosine of 3x plus c2 sine of 3x. Now we need y's of p, which is u1 y1 plus u2 y2. Now y1 is cosine of 3x, y2 is sine of 3x. Now we have to use Wronskian to find our missing functions u1 and u2. So first we're going to create this matrix W. It's a 2 by 2 matrix with the top row being my y1 and y2 functions. In other words, my cosine of 3x and sine of 3x. Now we need to find derivatives. The derivative of cosine 3x is negative sine of 3x times the derivative of 3x, which is 3. And then the derivative of sine of 3x is just cosine of 3x times the derivative of 3x, which is 3. Now, as before, we're going to find a determinant, which means I'm going to multiply these terms, giving me 3 cosine squared of 3x minus multiply these two, which is negative 3 sine squared of 3x. So notice what happens here. We have 3 cosine squared of 3x plus 3 sine squared of 3x. We're going to take the 3 out, leaving me with cosine squared plus sine squared, which is one of the Pythagorean identities. Cosine squared plus sine squared is equal to 1, which means this whole entire thing is equal to 1. So 3 times 1 is 3. So W is equal to 3. To find W1, I'm going to replace the first column with 0 and my function of g of x, which is 1/4 cosecant of 3x. Now the right side, or the right column, stays the same. So sine of 3x, 3 cosine of 3x. And now I find the determinant. 0 times anything is obviously 0, minus 1/4 cosecant of 3x times sine of 3x. Now cosecant is nothing more than 1 over sine, which means we're going to write negative 1/4. Again, cosecant is 1 over sine, therefore it's 1 over 4 sine of 3x times sine of 3x, which means sine of 3x cancels out, and we're left with negative 1/4 as my W sub 1. Finally, we find W sub 2, which is a matrix with the first column being the same as W, but the second column is replaced with 0 and the function, which is 1/4 cosecant of 3x. And again, the first column is the same, so cosine of 3x and negative 3 sine of 3x. And again, we're going to find the determinant, which is 1/4 cosecant is again 1 over sine, so 1 over 4 sine of 3x times cosine of 3x, or cosine of 3x over 1, and minus this times 0, which again is 0. So cosine of 3x over 4 sine of 3x can be written as 1/4 cotangent of 3x, which gives us W2, which is again 1/4 cotangent of 3x. Now we have everything we need to solve this. So U sub 1 prime is equal to W1 over W, which is negative 1/4 divided by 3, which is negative 1/12. That is U sub 1 prime. U sub 2 prime is W2 over W, which is 1/4 cotangent of 3x divided by 3, which means the same thing as multiplied by 1/3, which makes it 1/12 cotangent of 3x. Now these are my derivatives, which means now to find U sub 1, I need to take an integral of negative 1/12. So an integral of negative 1/12 with respect to x is negative 1/12 x plus c, but again, we're not going to write that since they cancel each other out anyway. Now we integrate 1/12 cotangent of 3x, and again, dx. We can take it 1/12 out, so integral of cotangent 3x dx is integral of cotangent 3x dx is 1/3 ln of sine of 3x, which we can reduce to 1 over 36 ln of sine of 3x. Now that we have U sub 1 and U sub 2, we can go ahead and plug it into my y's of p. So U sub 1 is negative 1/12 x times y sub 1, which was cosine of 3x, plus U sub 2, which is 1 over 36 ln of sine of 3x times the function y2, which is sine of 3x. Finally, the general solution would just be sum of y's of c plus y's of p, which is y's of c, which is here, c1 cosine of 3x plus c2 sine of 3x, plus my y's of p, negative 1 over 12 x cosine x 3x plus 1 over 36 sine of 3x ln of sine of 3x. Thank you again for joining me. Make sure you like and subscribe, and I hope to see you next time. Take care.